So when we meet a new family of functions, we're going to ask, what does its graph look like? What's its domain and range? And then our next question would be, has it got an inverse? And for odd power functions, those are one-to-one, which means that they definitely do have an inverse. But what is that inverse? Well, the answer is that we need a new notation to describe that inverse. To describe the inverse of a power function, we use what's called a radical. So for a positive odd integer greater than or equal to 3, so we're not going to do this for power 1, we define the pth root. We'll define this first as a function. F of x is the pth root of x. That's defined to be the function that is the inverse of x to the p. So thinking about that in terms of functions, x to the p and the pth root of x are inverse functions of each other. Thinking about it in terms of numbers, the pth root of x is the unique real number such that when I raise it to the pth power, I get x back. We call these radical functions. This symbol, the squiggly line, is called the radical. The number p, written here, is called the index. And the number x written inside is called the argument. When we write radicals by hand, we'll often write the little crook here really wide so we can tell that the index is inside it. And then we'll often put a little hook down at the end to make it really clear where the radical symbol ends, because that's going to have implications later for order of operations. So we can take some pth roots of numbers here. And there are lots of methods we can use, but kind of the most basic method for figuring out a pth root is just trial and error. So if we want to take, for example, the third root of 27, we can just guess some numbers, right? 1 to the third power is 1. 2 to the third power, that's 8. 3 to the third power, oh, we get 27. So 3 to the third power is 27. That means the same as saying the third root of 27 is 3. So that was just using trial and error to find the third root of 27. And of course, we can take those actual powers, 3 to the third, we can work out on a calculator if we'd like. Let's take the fifth root of 32. 1 to the fifth power, that's 1. 2 to the fifth power, that's 32 already. So that means the same thing as to say the fifth root of 32 is 2. And now here we want to take a fifth root of a negative number. That's perfectly fine, right? Because if we take a negative number to the fifth power, well, we get another negative number. And I'm not going to start at 1 here, because I know 2 to the fifth is 32. That's too small. I'm going to try taking negative 3 to the fifth, and that'll give me negative 243. Still too small. Negative 4 to the fifth, that's negative 1024. Still too small. Negative 5 to the fifth, oh, there we go. That's negative 3125. Which means the same as to say that the fifth root of negative 3125 is negative 5. So we've just found some roots using trial and error. That is, we tried taking various powers of numbers, until we found the one we wanted to take the root of. Now, that worked because all of these roots were carefully chosen so that the actual result would be an integer. That's usually not the case. In fact, roots are usually irrational numbers. If we have a root that's not an integer, we have several options. One option is to just leave it as is and just not do anything with it, just report whatever result we want as a root. Another option is to do what's called simplifying the root, which we'll discuss later. We can get a decimal approximation using a calculator, or we can get just kind of a rough approximation by hand using trial and error. So let's see that last one in action. We want to get a rough approximation. In particular, we're going to see what two consecutive integers each of these roots is between. Right, so consecutive integers, that just means like 2, 3, or 7, 8. Right, just one number and then the next number. So if we want to see what two consecutive integers is the third root of 45 between, we'll look at some third powers, right? 1 to the third is 1. 2 to the third is 8. 3 to the third is 27. 4 to the third is 64. Right, and 45 is between those, right? 27 is less than 45 is less than 64. So that tells me that the number whose third power gives me 45 has to be between the number whose third power gives me 27, that's 3, and the number whose third power gives me 64, that's 4. The third root of 45 has to be between 3 and 4. What about the fifth root of negative 18? Well, negative 1 to the fifth is negative 1. Negative 2 to the fifth is negative 32. Oh, but negative 18 is already in between there, right? Negative 32 is less than negative 18 is less than negative 1. So that means negative 18 has to be between the number whose fifth power is negative 32, so negative 2, and the number whose fifth power is negative 1. That's negative 1. The fifth root of negative 18 has to come between negative 2 and negative 1. And both of these numbers, 45 and negative 18, have the appropriate roots, right? These are numbers. But they're irrational numbers. And it turns out the best way to describe those two numbers in particular is to just say the third root of 45, the fifth root of negative 18. But there's no problem with taking those roots. Those roots are well defined. And in fact, if we have a radical function with an odd index, we can talk about its domain and range. Because if we have a radical function with an odd index, its inverse is a power function with an odd exponent. A power function with an odd exponent has domain, all real numbers, and range, all real numbers. Which means that its inverse has range, all real numbers, and domain, all real numbers. So if we have an odd index radical function, its domain and range are just all real numbers. We can put any real number in there. We can get any other real number out.